Let's begin today's lesson. Now, you've looked at networks, you've looked at how they're formed, the hardware we use across those, and we ended up with something called Ethernet. And the Ethernet protocol allows us to use the Ethernet cables, but there's a big problem there. The problem is that you can have things like collisions because you can end up with two machines with the same IP address. So today we're going to be looking at what the role of the CSMA CD protocol is in collision detection. We'll look at bit streaming, and we're going to begin looking at the differences between the World Wide Web and the internet. So quite a jam-packed session today. So let's begin. So let's start by looking at Ethernet and collisions. Now you might want to pause the video and have a look at the flow chart in a bit more detail. So study that and it'll give you an understanding of what's happening with the CSMA CD protocol. So it's possible that we end up sending data packets on the same channel at the same time, and that means two data packets can end up colliding, which is called a collision. Now carrier sense multiple access with collision detection, which is CSMA/CD, is a protocol that can help us resolve this, and the flow diagram actually takes you through the steps it goes through to prevent collisions. So make sure that you have the full form of CSMA/CD written up, because obviously that can lead to a mark. We're going to unpack this algorithm in a bit more detail now. So what actually happens is that you have a data frame, as we know from the Ethernet protocol, that's sent, and when it's sent down a cable, it changes its voltage. So the frame is assembled and it checks that if the line is idle. If it's not idle, then it'll wait for the allocated time before it starts transmission. Now normally what happens is that when a collision is detected, a node stops transmitting completely and sends a jam signal. Then it waits for a random amount of time and then starts retransmitting. And this random time period is also decided by the CSMA CD protocol. So if you're going through the algorithm, we've assembled our frame. Is the line idle? No. Wait for an allocated random amount of time. Then you start to send the frame. And you set the transmission counter to 1. So, okay, well, that's our first attempt, really. And then you detect a collision. So what happens? Is the collision detected? No. Well, continue sending. Is the frame sent? No. The process keeps on repeating itself. If it's sent completely, then it moves on to another frame. If there's no other frame, it ends. Otherwise, the whole process loops again. Assemble frame, it's line idle, and so forth. But what happens when there is a collision and it's detected? So the logic works as such that, okay, if a collision is detected, you stop transmission and send the jam signal. You increment the transmission counter because it's your second attempt and so forth until you reach the max transmission counter. If you reach the max transmission counter, then obviously you abort the transmission because the line is dodgy. That means you won't be able to transmit. There must be some serious fault on it. Otherwise, you wait for a random allocated time period and then restart the process of transmission, and hopefully there's no collision detected this time. It's pretty simple and a clever way of ensuring that no matter what cables, wherever they are in the world, the protocol can help avoid collisions. And this can also work for wireless devices as well. We just need to work out a mechanism of detecting transmission on the same channel. So you need to know how it all works, what CSMA/CD stands for, what happens when it detects a collision. It stops the transmission, it sends out a jam signal, it waits for a random allocated time period, and then it starts either retransmitting or it'll keep updating the transmission counter until it reaches the max transmission counter, and then it aborts the transmission. Now, that's all you need to know about CSMA/CD. Hopefully that is clear. Now let's move on to a bit streaming. So okay, we've got our cables, we've got our network connected together, and these days you can stream bits instead of downloading bits. And bit streaming is a process that allows you to have all the nice things that we currently enjoy in the form of YouTube and Netflix and whatnot. It basically means it's a contiguous sequence of digital bits sent over a network which requires a very fast connection like broadband or 5G or 4G. Now bit streaming can be on demand, aka YouTube, or it can be real time, like for example sometimes you have live streaming going on. Often video or large files are sent with compression, and there is some element of buffering which is also required for a smoother playback. Now, how do you do Netflix and chill? So basically you can look at it in any form. How do you use YouTube? So the reason sometimes when you're watching a Netflix or a YouTube stream and you get choppiness or lag, is that the transmission rate from the server to this thing called the buffer ends up being slower than the buffer to the media player or the browser. So what basically mean is that you might have a 100 megabit connection and your buffer only needs 10 megabit connection to have a smooth stream running through. But what happens is on that 100 megabit connection, sometimes you end up with, I don't know, a jam, a lot of issues with the bandwidth, maybe the server is slowed down because lots of people are connecting to it, and that 100 megabit connection ends up being 5 megabits. And when that happens, your buffer is getting emptied out a lot more quickly than the stream that is coming to it. So that means that you can't fill the buffer fast enough compared to how much you're consuming, and that's where the lag and the choppiness comes across. So if you're looking at that little diagram at the bottom, you'll probably see that the source of the data stream is bit streaming from the server, and the buffer itself is before your media player, and this buffer needs to be filled so you can enjoy a nice smooth playback. And if you're on the high end of the buffer limits, then it's pretty good, but when you start going below the low limits, then obviously things become a bit more strange. So let's look at this in a bit more detail. The larger the buffer, the better the control over the bitrate and the smoother the playback. So that's good. We need to have large buffers, but that requires a lot of memory space that we need to allocate to it. Now the media player will check the minimum and maximum values, also known as the low and high watermarks of a buffer. And the difference between both is usually 80% of the buffer size. Now if you're within that and you know it's pretty much good, your playback is okay, but when you start falling off the lower watermark, then obviously the issues become apparent. So what does it mean by on-demand bit streaming, for example, like YouTube? So in this particular case, a file is stored on a server, it's converted or encoded into a bit streaming format, like a typical MP4 or MOV file, because it probably uses some proprietary or custom compression and custom encoding to keep the file sizes or bandwidth impact down. Now a link to this encoded file is normally placed on the web server, which you download. So when you click on a YouTube link or you click on a Netflix image, that's basically what you're doing. You're downloading the link to this encoded file, and as the user clicks the link, the file is downloaded in a contiguous bit stream. That doesn't mean continuous, it means contiguous. So just be aware of the difference in those words. It is broadcasted to the user as and when required. It's possible to pause, rewind, or forward the video or the music if that's what you want to do. So it's something that we use all the time these days. Now real time, that's basically live streaming. And in this case, what's happening is an event is being captured by the camera or microphone, and the signal is immediately encoded into that custom format, basically which is a streaming media file. And this encoded file is then uploaded to a video streaming server. The server sends it to the user's device because they already have subscribed or signed up to watch this event. And since the event is live, it's not possible to pause, rewind, or forward it. Saying that though, there's sort of a hybrid streaming which is now possible. What YouTube normally does is it captures the live stream and then it saves it automatically as normal YouTube video encoding format. Now what happens is that you can't forward it because obviously the event is in real time, but you can pause it and you can probably rewind it. So that's possible as well. However, for the purposes of this particular exam, real time is pretty limited. You can't pause, you can't rewind, you can't forward it. Now we're going to move on to looking at the internet or the web. Do pause the video and have a look at the key terms. We'll be using these over this lesson and the next few. Of course, you know what an internet is. We use that all the time. Massive network of networks made up of computers and other electronic devices, and uses the TCP/IP communication protocol. Then you've got something called the World Wide Web, collection of multimedia web pages stored on a website, which uses the internet to access information from servers and other computers. HTML you know about, URL you know about from IGCSE, you know what a web browser is. The definition is there. Please make sure that you're familiar with that, so you're not writing things out from memory which might not be very technical. So just be focused on that. Now there's a lot of these key terms, so do pause it and do jot these down. And there's going to be the next set of key terms that we're also going to be introducing right now, which are things like the Internet Protocol, IPv4, classless interdomain routing. All of these we'll talk about. So it's quite an extensive next couple of lessons that are going to come up, which are going to be looking at everything from zero compression to subnetting to private IP addresses to public IP addresses, domain name service, JavaScript and PHP, which you're familiar with already. So some things which you know, some things which might be new to you. We're going to be covering all of that over the next couple of lessons. So do pause the video. This will take you a few minutes or so to jot a few of these things down. So make sure they are in your exercise book. Okay, hopefully you've got these down. Now, the next section, what I want to do is I want you to start looking at work that has been produced in an interactive activity which covers a lot of these topics that we look through, and hopefully it'll make more sense. So just to give you a bit of different flavor of what was happening in other classrooms, so you don't just feel a bit left out. Okay, so here what I did was I got a few students to come together with different topics related to the internet, and they investigated the infrastructure behind the internet itself and came up with the key points, which are then vetted by me, so the information is all in line with what the syllabus requirements are. So let's go through this particular one, and hopefully it'll make more sense. Okay, so how do you connect to the internet? Well, you need to have some kind of setup behind the scenes. So you've got your devices, you've got your network. How does that connect to other networks? Sometimes it uses devices such as PSTN, which basically is a public switch telephone network. And these systems are your big mega corporations, often government companies that control the telephone network. And it's a circuit switch type system, which basically means that the wires are switched depending on the location of the call. So you create a path between two devices, and data travels that way. Originally they were arranged into hierarchies so that if a call couldn't be handled in a local cluster, basically a local set, then it was passed to a higher wire for different routing. So you have different paths and high priority, low priority, but that's all changed now. Everything is equal in that case. The routes are much more organized and efficient, and that's all thanks to the use of fiber optic cables and microwave transmission links, which allow you to communicate with anyone, anywhere using a public telephone network. However, the biggest problem with this is wasted bandwidth. So think about it this way, that if you are reserving an entire circuit for a particular call or a data transmission to happen, then even if you're sending 1 megabit of data and the line has a capacity of 100 megabit of data, 99 megabits is wasted. So it can become tricky. Now, questions you've got to think about is what is circuit and packet switching, and the next solution to this was how does another technology called voice over internet protocol, or VoIP, how does that eliminate the bandwidth wastage that comes with PSTN? So in this particular case, what happens is that you just need an internet connection, and then you need a microphone to record the sound. That's because it's voice over internet protocol. Now, obviously, you can also do video over internet protocol as well. But voice over internet protocol allows us to do all sorts of stuff like video conference, but it requires specialist hardware. So you just don't need a telephone receiver. You need webcam with a microphone and a computer as well, and maybe a router and all of that. The VoIP client is normally a software, and this program handles the translation and transmission of audio or video data, which usually happens in real time. And it uses packet switching, which means data is divided into smaller packets and then sent through any possible route. Now, this is the reason why you end up avoiding that bandwidth wasted with PSTN. So the connection is live only till a person is speaking. And so think about this. If we were talking on a telephone call, the connection will be live all the time. But using VoIP, the connection is only live when I am talking, and the moment I stop, somebody else can use the line. And it's pretty clever because it's using data packets, and that helps eliminate wastage of bandwidth. The recorded sound obviously is processed and turned into from analog to digital, which we know already. So there's an ADC, which basically might be the modem or the router involved in that particular place. Of course, you can then also have things like cellular networks. These are the cell towers, And what happens is that you have these towers which are joined together in the form of a grid, and they provide radio coverage over large areas, which allow portable devices such as mobile phones to communicate with fixed transceivers and telephones across the network. So you will have a combination of cellular networks and PSTN, and you might be using VoIP technology to eliminate bandwidth wastage along the way. Now each cell tower uses a different set of frequencies from its neighbor to avoid interference, and what they want to do is get a better bandwidth connection made, and that's where you can have cell towers which are often 2G, some are 3G, some are 4G, and now obviously 5G ones as well. Lots of different sets can be made, but we don't need to know about these sets at all. Now the advantage is these consume less power, increase capacity, distribute to larger areas. You don't need to kind of put cables all over the place. So there's benefits for cellular networks as well. But the problem with cellular networks themselves is that they require kind of like line of sight. And sometimes if you want to talk to someone on the other side of the world, they can become a bit more tricky because cellular networks have to deal with the curvature of the Earth. So it might be that the signal just ends up going out to space. And this is where satellite comes into play. So satellites are objects that revolve around the Earth, and they have a benefit of having a vantage point or a viewpoint at the top. So one cell tower can directly see that, and another from on the other side of the planet can also directly see that. So there can be three different types of satellites. You have the geostationary one, the medium Earth orbit, and the low Earth orbit, and each one requires a different type of coverage. For example, you might have the geostationary one, which is fixed, which allows 2 points on the planet as they rotate. They're going to miss this geostationary object because it's just stationed at that one point in space. But what that satellite can do is provide coverage to a lot of other areas as the planet is rotating. Then you have the ones which are in medium and low Earth orbit, and they rotate with the planet, and they allow you to just follow the two cell towers all around the world. So different benefits of each. Now the advantages is obviously higher bandwidths are possible. They cover larger areas than cell towers could ever cover. But the disadvantage is that they're very high cost. It's very difficult to send satellites into space, and the bandwidths are obviously used up all the time. So just be aware that there are pros and cons of each type of technology behind the infrastructure. Okay, so that takes care of the infrastructure itself. But how do we know where every single device is and how these devices can connect to other devices and send and receive data? So we use IP addresses for that. So these Internet Protocol addresses, you're familiar with them from IGCSE. However, we're now going to go into a bit more depth into what IP addresses are all about. So there are two kinds. The first one is IPv4. That's the version 4 of the Internet Protocol, and then the other one we're using right now is IPv6, which is the version 6. And what basically happens is, the story of computer science all along is that at some point we decide, well, you know, we're going to have Internet Protocol addresses and we're going to make them 32 bits because nobody in the world will ever have billions of devices that can connect to the internet. And so the designers at that point in time decided that we're going to have a 32-bit size string of numbers which is assigned to every device when it connects to the internet. And they're all going to be unique, and they're all going to be formatted in 8-bit segments, and you get something like 105.255.1.1 and things like that. However, then technology became so useful that mobile phones came along, smart fridges, Internet of Things, you name it, every single device required an IP address, and we ended up with more than billions. So 2 to the power of 32, that's how many unique connections you can have. You can't have anything more than that. So then we moved on to IPv6, which was developed to overcome some problems that IPv4 had. So it uses 128-bit addressing, and because now the bits are so long that if you try to you won't be able to fit them on screen if you try to put them together, they decided, well, we'll convert them into hexadecimal, so you know that each hexadecimal digit is equivalent to 4-bit binary, so they're broken into 16 chunks to make it manageable. Okay, now fine, that works really well at the moment, but I think at some point in the future, you know, we might need to go and upgrade this once again. So this IPv6 was designed to allow the internet to grow in the number of hosts and the number of users or clients. Now, the benefits it has over IPv4 are that it removes the risk of private IP address collision and has built-in authentication as well. So there's no need for something called the NATS, network address translation. So you don't actually need that because every device is unique as well. However, the issue with IPv6 in particular is that the number of zeros can be a huge amount. And even when you're looking at hexadecimal digits, which are broken into 16-bit chunks, they can also be quite huge. So a method to compress large IPv6 addresses is known as zero compression. And what happens is this, that if you have a string of zeros in an IPv6 address, then you will compress it by eliminating the zeros by just putting an extra colon in the place. So if you're looking at the example that's on screen towards the end, you'll probably see that there's a number called 2221 colon 000000000000000000 colon 1312 colon 0812. Now, when you have that, we can just simply compress it by simply saying 2221 colon colon. That means there's a string of zeros, and the last few digits are 1312 colon 0812. Now, this allows you to take IPv6 address, which might be 36 bytes long or something like that, or 36 characters long, and reduce it to about 12. And that makes it much more easier to read on screen as well. However, the issue with IPv4 was that it's got a limited amount of IP addresses that it could use, even though it's in billions, but they're still running out. So a technique like subnetting is used to divide a LAN into perhaps 2 or more smaller networks and then use IPv4 addressing systems. Now, this helps reduce network traffic within the LAN in the first place, and it's beneficial because you can use techniques like organizing net IDs and host IDs to make the network less complex. So I'll give you an example of that. Let's say, for example, we have a school. The school's given one IP address by the ISP instead of 1,000 devices that might be part of the school network. So what happens is that one IP gets sent all the traffic that the school uses, and then within that IP, you can then have a subnetwork which uses a different range of IP addresses. So we kind of like cheat the system in a way. Now, the host ID might be unique, but the net IDs might be different, and you try to do that to reduce complexity in the overall internet network range that might be out there. So net IDs are an ID for different departments in the school. So maths might also have one, humanities, computer science department might have one, and host ID is basically the ID that the users in each department use. We can split an entire network into net IDs and host IDs, and we can also apply that to ISP level as well and beyond. So it increases the number of devices we can use in IPv4. Now let's start looking a bit more deeper into the possible issues that might come across with IPv4. So we know that it's based on 32 bits, giving us a possibility 2 to the power of 32, which is about 4 odd billion possible addresses. Now we can be a bit more clever, and what we can do is we can divide this into different network classes. So you have a class A, where you allocate 8 bits for your company ID or net ID or department ID, and then you have 24 bits allocated for host IDs. And what that allows us to do is create some very large networks. 2 to the power of 24 is a huge number of devices. So think Google, Amazon, and all of that, international organizations that could use it. And they might allow you to have 2 to the power of 24 host IDs available to them. So lots of computers, but you can only have 256 2 to the power of 8 organizations. So not a lot of big companies can benefit from it. Then we have class B, which allows you to have 16-bit net IDs and 16-bit host IDs. And that gives us 2 to the power of 16, which is 65,000-esque companies and 65,000-esque host IDs. So that means a lot of companies can fall into this particular bracket. So that's pretty good as well, you know. But again, not a huge amount. Obviously, there are millions of companies around the world. And then you have the class C, which allow you to have a smaller number of bits, 8 bits allocated for your host ID. That means you can only have 256 computers, but then you have 24 bits allocated towards net ID, which means a lot of organizations there. But this can also lead to a problem. That, think about this, that if there's a company that has 284 machines, they would need to subscribe to a Class B license, which allows them 65,000 machines, but they're not using all of that. So those IP addresses or licenses can get wasted as well. So this is where a solution like classless interdomain routing, or CIDR, comes into play. This reduces the problem by increasing the flexibility of the IPv4 system. So you use a suffix such as 192.30.250.00/18, which means a further 18 bits will be used for the net ID, and the last 14 bits will be used for the host ID, rather than the normal 24 bits and 8 bits for a Class C network. So that gives us a bit more flexibility, that we don't need to reserve ourselves to just simply Class A, B, or C. We can just use the slash and say, well, out of this, we're going to use 18 bits for our network IDs and 14 bits for our client or host computers. And that flexibility is very, very important. So the suffix clearly increases the flexibility regarding which bits represent the net ID and which represent the host ID, instead of just fixing us to a particular class. And that's what classless interdomain routing is all about. Now I'm just going to come back to zero compression for a moment. That IPv6 addresses also have problems with zero compression. So think about what we were talking about in zero compression. IP addresses are quite long, and we shorten them using zero compression by eliminating the zeros and just putting a colon in its place. So you have a double colon to identify a string of zeros. Now this can only be applied once to an IPv address. So for example, if you end up having two sets of zeros separated by a set of digits in the middle, you can only change one set. And that basically means that we have no way of knowing what the original address was, because it can be very difficult to tell how many zeros were replaced on each occasion. Therefore, zero compression can be quite ambiguous, and you just got to be aware of that when you're using it. However, that's not the only thing that can help us with organizing a network. You also have things like private and public IP addresses, and these are quite useful for us to set up zones which can be secure and something where we can share and collaborate. So let's look at public IP addresses first. Public IP addresses are IP addresses allocated by your ISP. So chances are that you have one which your home internet provider gives you, and it identifies the location of your particular device on the internet. It's used to get internet service for you, and it's controlled by the ISP. You can't change it. You can have two types of these. One is called static IP, which means devices assigned to this address, their IP address does not change at all. And then you have dynamic IP, and that basically means that devices assigned with this address, these IP addresses change over time. So the next time you connect to the ISP, it's not the same. And static and dynamic IP addresses also apply within a network. So it might be that your router is allocating dynamic IP addresses, or you end up being given static IP addresses by your network manager. And obviously that's one of the reasons why you end up with that Ethernet conflict that we were talking about earlier. Now, private IP addresses allow for an entirely separate set of addresses within the network. They allow access to the network without taking up a public IP address space. However, devices using these private IP addresses cannot be reached by internet users. So think about this at our school. The school has that one IP address that the ISP has given it. So if somebody wants to connect to you, who's part of the school network, they can't, because your particular IP is hidden behind the school firewall or the school gateway or router or whatever device is using to connect to the ISP. So as far as the internet is concerned, there's only one school, and then within that school you've got a whole subset of net IDs and host IDs using private IP addresses which allow you to connect multiple devices. And that's another clever way of extending the network range, especially if you're using IPv4. Now also remember that Class A, B, and C also apply to private IP addresses. So Class A organization might end up using 16 million addresses or 16 million clients. Class B could use 1 million possible addresses, and Class C can use 65,000, I think 600 possible addresses as well. And it's another clever way to extend the network by using both a combination of public IP addresses, which is just one address on the internet, and within that IP address, you can use the whole network range all over again. So, pretty clever way. Now, the final bit we're going to look at is how do we connect, once we know our IP address, how do we connect to the server and display web pages? So you would know about URLs from IGCSE. The Uniform Resource Locator is another form of ensuring that the IP address is very easy to remember by humans. Nobody wants to remember a string of digits. So we come up with a methodology where you can use a domain name service to find out what the IP address is by just simply typing in an address like www.google.com. Now, web browsers are software, as you know, that allows users to access and display web pages on their screen. So they basically interpret HTML data which is sent from these websites or servers and display the results. So web browsers often use these URLs to access websites, and generally you will normally have a protocol, the website address, the path, and the file name. So something like HTTPS is the protocol, www.google.com is the website address, and then you might have index.html or whatever else, that a file that you need to access as well. The domain name service, also known as the domain name system, gives domain names for internet hosts and is a system for finding IP addresses for a particular domain. Now, these eliminate the need for users to memorize IP addresses, and it's kind of like a matching service. So you type in an address, it will find the IP address by connecting to a DNS. So the process, if you remember from IGCSE, was that the web browser connects to the web server directly. Well, it doesn't. The web server will probably connect to a DNS server once, and the DNS server will say, well, okay, do I know this website's IP address? And if it does, it sends it back. If it doesn't know it, it then connects to the next DNS server in its cachement area and says, well, okay, do you know this website's IP address? And if it does, it sends it back to the first DNS server, and then that passes on to the computer. So that process repeats continuously until you find the IP address. Now, if a DNS server can't find the address in its database, it'll send that information, that address not found, which can happen if the user mistypes the URL as well. The computer will then connect to the website server because it now knows its IP address, and then the communication begins, which basically involves getting HTML data being sent from the server to the user's computer. The browser is then going to translate it and display it on the screen for the user to interact with. And what basically happens is that you will end up using things like HTML scripting and JavaScript and PHP, which we'll probably look at in the next lesson in a bit more detail. It's a bit of a long lesson for today. So do pause and rewind if you need to, and do ask questions if there are things that you're not sure of. Do take your time in understanding the role of subnetting, the role of CIDR, and so forth. And you should be able to understand what the difference between on-demand and real-time bit streaming is now. You should be able to talk about the differences between PSTN and VoIP. You should be able to explain the differences between public and private IP addresses and why we use them, and how does CIDR expand on things like subnetting as well. And next lesson, we're going to be looking at HTML scripting, so hopefully a bit of a hands-on lesson for you. As always, if you do find something a bit confusing, do get back to me. I'll see you in the next lesson.